Right, this represents the first of a multi-part video series that I'm doing on the derivation and interpretation of the quasi-geostrophic framework for meteorology. My name is Matt Burek, and a little bit of my background. I have a bachelor's degree in oceanography from the U.S. Naval Academy, as well as a Master of Science in Meteorology from NC State University. I served as a military instructor of meteorology at the U.S. Naval Academy from 2016 to 2022. And I taught the whole spectrum of meteorology courses there, from intro to meteorology through atmospheric thermodynamics, through the first of our 2-semester dynamics sequence, as well as the electives, synoptic meteorology, tropical meteorology, and severe storms and tornadoes elective. And I'm also a 20-year retired naval aviator. Some of the references that will be used or drawn from to some extent throughout this are some familiar ones there at first. Holton's 2004 4th edition Intro to Dynamic Meteorology, Gary Lackman's 2011 Mid-Latitude Synoptic Meteorology, and I'll particularly give that credit for one of the examples that is used in interpretation of the QG geopotential height tendency equation. Course notes from NC State's course MEA 705, Dynamic Meteorology, which has been taught for many years by Walter Robinson, and who I was privileged to take that class with him in 2011. Lots of personal correspondence through the years with my Naval Academy colleagues, Beth Sanabia, Brad Barrett. And finally, I would be remiss if I did not give credit for the stylistic inspiration of this presentation for my wonderful NC State professors, Sandra Uter and Matt Parker. And most of this presentation is a slightly adapted form of what I taught in the USNA elective course, Synoptic Meteorology, our 400 level advanced elective there. So without too much further ado, a few assumptions here at first, and I won't read through every one of these, but it's assumed that the viewer of these videos has some familiarity with basic meteorological variables and dimensions, has taken a basic undergraduate atmospheric dynamics class where we've covered down on these topics, a basic undergraduate atmospheric thermodynamics class covering down on these topics, and finally familiarity with advanced calculus, vector notation, multiplication, partial differentiation, gradients, as well as curl and divergence. So for the individual who has seen some of this before, this should be relatively easy to follow. And this is a full derivation, by the way, and interpretation of a lot of the equations along the way. So I do not intend to really skip any steps in this process. This is the full worked out everything from beginning to end to arrive at the 2 major QG equations. So a little bit of an overview of the process. The progression goes more or less as follows. The first thing that we'll do is to write down the simplified Eulerian momentum equations in isobaric coordinates. And on the last slide, I mentioned that it's nice if the viewer has some familiarity with using pressure as a vertical coordinate, but even if you don't, it's fairly easy to follow. That's the vertical coordinate that we're going to be using throughout these derivations. So step 1 will be to translate the momentum equations in Cartesian coordinates, which is what they're typically derived in at first in dynamics class, and translating those to isobaric coordinates with a few additional simplifications along the way. That'll be step number 1. Step number 2, from those 2 momentum equations, we will write a simplified vector version of the momentum equation. And having done that, we'll partition that into geostrophic and ageostrophic parts to get the QG vector momentum equation, which will involve some additional simplifications and some scale analysis along the way. Once we have arrived at number 3, we will take the curl of equation 3, the curl of the vector momentum equation, specifically just the vertical part of the curl of the vector momentum equation, in order to derive the QG vorticity equation. And that'll be a little bit of a hard stop, at least with this first process that we walk through here. So the steps 1, 2, 3, and 4 are all kind of from a constant stream of development, starting from things that would have been derived in basic dynamics all the way up to this QG vorticity equation. And we'll do some analysis and interpretation of the intermediate steps along the way as we walk through that. Once we get to number 4, we'll kind of pause on that particular avenue and we'll step aside from dynamics over to thermodynamics And starting from the first law of thermo, we'll ultimately derive the QG version of the thermodynamic equation. And now that we have equations 4 and 5, we'll be able to combine them together to derive two very important equations, the first of which is the QG geopotential height tendency equation, and the second of which is the QG omega equation. And we'll do quite a bit of analysis on both of these, and not only what they are and what the terms mean, but how they relate a little bit to the real world with some examples as well. So the fundamental idea behind all of this is that atmospheric flow above the boundary layer, at least, is mostly close to a state of geostrophic balance. That is, it is pseudo or quasi-geostrophic, and thus has a characteristically small value of Rossby number. With that idea in mind, and with the assumptions that we will detail along the way, we will simplify and combine the governing equations, many of which are tied into this steps 1 through 7 up here, in ways that both retain the fundamental dynamics, we're not going to sweep those aside, but that also at the same time, and very importantly, offer understanding, physical understanding of the processes that lead to two different things. One being vertical air motion, and that's what the QG omega equation is going to give us. And the second being weather system development, movement, and decay, which is what the QG geopotential height tendency equation is going to give us. So for the most part, the examples that we'll do along the way will focus on the synoptic phenomena that are most important to day-to-day weather and forecasting, including extratropical cyclones. At the end of this, we'll go through an entire look at the cyclogenesis process from the QG perspective. Also, frontal systems, upper level waves, and jet streaks. And we won't talk much about fronts in this particular series of videos, but we will go quite a bit into some depth on jet streaks and the 4-quadrant model of jet streaks as we work through this. And fundamentally, QG is bringing together the ideas of describing the atmosphere with equations of motion, which are derived in basic dynamics, the use of scale analysis to determine dominant terms in the equations, the maintenance of balance by secondary ageostrophic circulations, as well as vorticity dynamics. So all of these disparate topics that are covered in some extent in dynamics classes are tied together in this framework very, very nicely to give us a way of understanding the large-scale mid-latitude atmosphere. So without any further ado, the first video here will just deal with deriving the two momentum equations in the Eulerian reference frame in isobaric coordinates. So probably somewhere before you've seen two equations that look something like this, and these would be our x and y momentum equations on the rotating Earth, where we have on the left-hand side here indicated these two total derivatives by the capital D over dt, and you may have referred to these as total derivatives. Some people refer to these as material derivatives or perhaps substantial derivatives. But all this basically is it combines a local change in the u wind and the v wind together with the advective tendency in 3 dimensions. So the east-west, north-south, and up-down advection of u and v. And we're going to break these total derivatives apart here in a moment in order to translate this to the Eulerian reference frame. On the right-hand side, the first term in both equations is the pressure gradient force. This is the zonal component of the pressure gradient force, where rho is density, p is pressure. And in this equation, this is the meridional component of the pressure gradient force here. The next terms to the right of that in each equation are the Coriolis terms. This is the Coriolis torque on the meridional wind, which acts in the zonal direction as an acceleration. And this is the Coriolis torque on the meridional wind, which acts, this is the Coriolis torque on the zonal wind, which acts or acts as an acceleration in the meridional direction. And then the final term, F sub x and F sub y, just represents a friction force in both of those equations. So if we expand out the total derivatives on the left side and write in Eulerian form, expanding the total derivatives gives a local tendency term as well as 3 advective terms. And so we get that in the first equation, breaking capital du over dt into this term here, as well as the first 3 terms on the right-hand side. And the first 3 terms on the right-hand side were moved over from the left, which is why they now have minus signs in front of them here. So this is the zonal advection term, the meridional advection term, and the vertical advection term. And then we also have, once again, the pressure gradient force, the Coriolis force, and the friction force. So that's what the zonal momentum equation becomes. And for the meridional equation, it looks quite similar to that by doing the exact same process, expanding the total derivative over here, moving the advective terms to the right-hand side. There's two additional things that we will do to finish step number one in this process. It is possible that in a class somewhere along the way or somewhere you may have established that the horizontal pressure gradient force in height coordinates can be re-expressed in terms of the geopotential that is expressed in isobaric coordinates by this transformation. So the vector form of the horizontal pressure gradient force here can be written as negative del phi over here, where phi represents geopotential, and that is just gravity times height. And so with that in mind, we can break that into that vector form into the two component forms, which would look something like this. On the left-hand side, the pressure gradient force breaks up into the zonal component term and the meridional component term, written in standard basis form here with I hat, J hat. And on the right-hand side of the equal sign, del phi breaks up into the components partial phi, partial x, I hat, partial phi, partial y, j hat. So we'll just make those substitutions and substitute in for the pressure gradient force when we rewrite or recast these two momentum equations up here. And by doing that, we are transforming from the Cartesian reference frame to the isobaric reference frame. And we're also going to throw in the simplification that the flow is frictionless. So we're going to drop off the two friction terms here on the end by assuming that we're above the planetary boundary layer. So for the zonal equation, partial u, partial t, we retain the first two terms. They don't change at all on the right-hand side. The third term changes a bit because now we're in pressure coordinates and not in height coordinates. So we don't use w anymore, which would be dz dt. Instead, we use dp dt, or a change in pressure with respect to time, where we're using pressure now as the vertical coordinate. And dp dt is the notation that we use for dp dt is the Greek lowercase omega. And so we have substituted that in for w. And the partial derivative is not with respect to z now, but with respect to p. And for the next term in the zonal equation, we don't use the pressure gradient force term that we had up here, but we use the I hat component of the geopotential gradient now. So negative partial phi partial x becomes the next term. And then finally, the Coriolis term does not change, plus f times v. And for the meridional equation, it looks very much the same. The first two terms, again, do not change from the representation that was up here. The third term, we don't use w, we use omega now as dp dt. And partial v partial z translates into partial v partial p in the isobaric reference frame. We again make a substitution for the pressure gradient force here by using the j hat component, so negative partial phi partial y, and the Coriolis term again just carries down negative f times u. And once again, you notice both of these equations we've dropped off the friction force by adding the first of many simplifications in the QG system, which is the simplification of frictionless flow. And that is it. This represents step number one. These two equations, partial u partial t and partial v partial t, represent the Eulerian momentum equations in the isobaric coordinate reference frame. And so we have satisfied at this point step one of the 7-step process that we're going to go through. In the next video, we'll work from step one and put those two equations that we just derived together into a simplified vector momentum equation, and then pause to do a little bit of analysis on the meaning of each of those terms.